Good afternoon. My name is Howard Stone. Welcome to the 2022 Holiday Science Lecture, an event we've been running every year here for a number of years. This program was put together by a number of people. It was a real team effort. I want to introduce a few of them to you right away. Dan Steinberg, Janine Nunes, Paul Canillo, and Nikki Abbasi, and some colleagues from Harvard. The story we want to tell is a story about our planet and a theme that you read about in the paper, the climate. And so twice during the lecture, we're going to invite the children up to sort of act out molecular ideas that we're trying to share with you that are important to the science of what we think about when we think about our planet. The theme of today is the world is a remarkable place. It's truly amazing. And we're going to hopefully tell you some ideas that you've never thought about before and or observed before. And I'm sure this is true for many of the children. It's probably true for many of the adults, and may be true even for some of the scientific adults in the audience. And we have a set of demonstrations that we're going to do for you live, so you really see that the kinds of things that are talked about in the paper for what you need to think about if you want to think about the planet and Earth and the climate. Who's this man? Albert Einstein. So there's this nice quote from Einstein who says, "In the matter of science, the first lesson should contain nothing but what is experimental and interesting to see." So when you or your parents signed up, we asked you to tell us some of the words you think about when you think about the Earth and climate. And you gave us this set of words. So during the lecture, you're going to see many of the words appear. You're going to see the word warming appear. We're going to talk about the globe. In fact, we have for you, to help you think about the Earth, we have some nice balloons about that. You're going to see why we think some things are changing in the world we live in. You're going to see that the word carbon comes up a lot. We're going to talk about the role of the ocean. So many of these words will appear. For the kids in school, you're learning science, and in this talk you'll see why many of the themes that you learn about in science are important. So where we begin is with some basic science. For the children in the audience, what is this called?
The periodic table.
Yeah, look at that. It's called the periodic table. Let's see how good you are with what the names of the atoms are. So if someone asks you, what's He? You say helium. How about C? Carbon. Carbon will come up a lot today. H? Oh, you're doing pretty good. N? Okay, there's a hard one. P? Well, at Princeton, P is Princeton, okay? But for the periodic table, it's phosphorus. And how about O? Oxygen. So these atoms will come up today. But the atoms aren't the whole story, because atoms can get put together into molecules. And small molecules are small groups of atoms. And so the simplest ones you hear about are carbon dioxide, O2, which is oxygen, that's the air we breathe, hydrogen, H2. You also hear about water vapor. And if you put small molecules together, you can get even bigger molecules. A crystal would be like the salt you put on your food. But for today's talk, the really important molecules are going to be carbon dioxide, and we'll talk a little less, but you'll see why it's important, water. They're very important when we think about the world we live in. And we'll hopefully be able to illustrate that to you. In the history of our world, this is a very famous photograph. This photograph was taken from space by 3 American astronauts. And the first time people were able to take a trip around the moon in 1968, and this photograph, which was so impressive to them, they labeled Earthrise. It's the first picture ever taken of Earth from space, and you see this beautiful planet on which we live. And a few years later, another beautiful image was taken from space that illustrates many of the features of our planet, and it was given the name the Blue Marble. Now, you see our Earth. You see our planet. What are some of the things you see in this image? Young man. Water. Perfect, yeah. And where do you see the water, by the way? In the ocean, right. So the oceans are clearly evident on Earth, on the planet. What about, yeah, young man, green? Clouds, you see the clouds, all the white features. Anyone else? Yeah. What was that? Land, you see the continents. Anyone else? Young lady in purple? Oh, you're good. So she sees a little bit of ice on the top. So we made our list also, and we said, well, there's land, you can see the continents, you can see water in the oceans, water's trapped in the ice. The technical term for ice is cryosphere. You see, people mention clouds, and the Earth is wrapped in a layer of gas that we refer to as the atmosphere. If you look hard under here, you can identify North America. If you look a little harder, you can see Central America. And if you have really good eyes, you might be able to find Princeton. Okay. Next thing I want to point out is there's a relationship between the words weather and climate, but they are different. And so we just want to briefly say to you how we think about them. So this morning it was raining. There was a sudden event in Princeton. That's a weather event. It started to rain suddenly. We think about weather as short-term events that affect our day-to-day life. We think about climate as happening over a much longer time scale that affects us over the period not of days, but of years. So weather you tend to think about as changing pretty quickly. The climate is what we expect to happen over a period of a very, very long time. So there's a common phrase people say that climate is what you expect to happen, because it's what we think about happening over long times, whereas weather is what you get. All right, so if you want to think about this a little more, you could say, well, what happens in Princeton? So you could say, I'm going to make a graph. We're scientists, so we illustrate things with pictures. I'm going to make a graph of the day of the month. So we looked up the weather in November in Princeton, the past month. And on the vertical, you could put the temperature. And in Princeton in the last month, it looked like this. This October is indicating the last day of October, and then November 1 goes forward to today. And you see every day it goes down and up. The minimum on any given day is at night. The maximum on any given day is during the day. So the weather is always changing. And it always fluctuates around, and that's a natural thing. You expect things to be changing in some somewhat random kind of way. That's typical of the weather that we see. So to illustrate some of the features on Earth that create the life on our planet, and I need you to think a little about the fact that we live on a spherical planet, and as several of the children said, there are oceans, and there's an atmosphere around us. We have a little experiment that's going to try to illustrate to you some of the features of a body that has a lot of water. So we have a tank with water. Nikki and Paul have been heating the left-hand side with a hot lamp that you can see. We're going to add a little ice on the right. Think about the ice as, say, the Arctic or the Antarctic. Think about the heat as, say, the equator. And now we're going to put in a little dye to ask what happens on the hot side, and we're going to add a little blue dye to ask what happens on the cold side. And then because there's air above it, which you might think about as the atmosphere, we're going to add a little Halloween fog and to just mimic what happens above this system when you have a gaseous layer. And you see some motions happening that are tied to the idea that it's hot in one place and cold in the other place. So if you look in the water, where does the hot water flow? The hot water flows along the top. Where does the cold water flow? On the bottom. So if you think about this as a mimic for Earth, then you can expect a typical circulation in between the hot parts and the cold parts. And you also see that the air rises on the hot part and then flows over the top and also creates motions in the air above. You can think about those as being somehow tied to the winds. Great, okay. So that was our experiment. Remember, there was a hot side and cold side. So if I ask you, this was a demonstration. How might this relate to planet Earth? What might you think is playing the role of the hot side? Young man? Yeah, it's cold. Antarctica's down on the bottom. And in the Arctic, it's also cold. Where's it warm? All the way back in the orange shirt? In the equator. So you can think about this experiment as telling us something about the differences that happen between the equator and the North or South Pole. So if I ask you where does the energy come from, to start this, it doesn't come from a heat lamp, but the energy that affects us, where does it come from? Anyone shout it out. The sun. Okay. So the sun is responsible for delivering energy to the Earth. Now, for the sake of just starting out, I'm going to say that energy is being delivered to the Earth. Some of it intersects the clouds and gets reflected. That's what we would say. Some of it makes it through the clouds and land on Earth. It's absorbed by the land. And the Earth emits some energy. We talk about that scientifically. We'll say that it's radiated. Some of it is emitted. Some of it makes it out to space, because that's all there is out there around us. Some of it intersects the clouds. So to understand that there's really energy involved, I need a volunteer, so I'm going to ask Alex Glazer, if you don't mind, to come down. Alex, sorry, you're an expert on campus on many technical things. I need your help. This lamp, I don't want children near. It gets rather hot. But to make clear something, I just want you to hold your hand above it and tell everyone what you feel. Say it louder.
It's warm.
It's warm. Okay. So the idea is that there's really energy coming from the lamp, and it travels, and it makes his hand warm. Okay, thank you, Alex. You can go back. I said it was a... Okay, so what is it about that energy that we're now going to talk about? For the next few minutes, we're just going to say energy is transferred. The sun is delivering energy to the Earth. Now, if you like pictures and you want to understand a little bit more about weather and climate, you can find pictures like this on the web. One of the young people said, oh, the equator is where it's warm. We saw in our little demonstration that where it's warm, you can expect hot air to rise, and then it starts to circulate. So some of the pictures that we sketched in our little demonstration are consistent with some of the features that you see when you look in detail at the way the atmosphere and ocean move on planet Earth. We're going to, in a second, ask some children to come down to help us with something. So let me just make two remarks. The first one is, energy is coming from the sun and is going to Earth, okay? So what we're now going to try to do is first ask some children to come up. I think we're big enough. If you want to come up, just come down front and stand on the left side over here by Dan Steinberg. All right. Okay, we'll stand down over here. For the parents in the audience and maybe for the children if you're listening, we're now going to try to illustrate what sets the typical temperature of our planet and why it has the typical, if you like, temperature of our climate that we get to live in. So for the children, I want you to look at the screen. Okay, so the first thing I want you to notice, for this exercise, you're going to be energy coming from the sun to the Earth. Okay, now sometimes your energy, you get absorbed by the Earth. That makes the Earth warmer. Sometimes you get reflected back into space. For this exercise, we're just going to ask you to walk in a circle around the stage in a straight line. So first, let's get in a line. Okay, and now the idea we're going to have is, when the parents look at the stage, when they're children in the audience, when they're children in the middle of the stage, we're going to say that that's the temperature of our climate system. That's the temperature of our atmosphere. So if there are only a few of you in the middle of the stage, it's very cold. And if there are a lot of you in the middle of the stage, it's very warm. Is that okay? Okay, so what I want you to do, what's your name? Nina? Okay, I want you to start to walk to Janine and then walk in a circle. So walk in a nice, leisurely pace. And what we now say, because we see a typical number of people in the atmosphere, is that the atmosphere has a certain temperature. Energy is being delivered from the sun to the earth. These are the carriers of the energy. Now, it's possible that as this energy is coming towards the earth, it's intercepted and it not as much makes it to earth. So slow down, keep walking, but go slower. And if the amount of energy getting to earth is reduced, go further down that way, walk to Janine. If the amount of energy getting to earth is lower, then the temperature goes down. And if a lot of energy is delivered to Earth, if you guys now go really quickly, then when you go really quickly, you can see they're okay molecules, that's the best molecules. If they go really quickly, there are more people in the center of the stage, and when there are more people in the center of the stage, the temperature goes up. And so this is a mimic of what's going on, because energy is getting delivered to our atmosphere. If a lot of it is there, it's warmer. If less of it is there, it's colder. So everything starts with the sun and energy coming in from the sun. We're now going to try to show you experiments that help you recognize and understand and appreciate that the energy from the sun is carried in the form of radiation, and we're going to tell you a little about it. So, in the atmosphere is CO2, carbon dioxide. There's not a lot of it. There's only a little of it. So I get to tell you a little about the story of CO2 while we also tell you about energy from the sun. So I'm going to start with carbon dioxide, which many of you have heard about and you read about in the paper. So starting in the late 1950s, so I was born around that time, to today, people have measured the carbon dioxide concentration in the atmosphere. It's a direct measurement. And it started in the late 1950s as it was at what was called 300 parts per million. So if there were 1 million molecules in the atmosphere, 300 of them were CO2. Today, that number is close to 420, and it's been going up like you see here, and it oscillates. Okay? So you can ask, oh, and this is called the Keeling curve, by the way. It's a curve. It's called the Keeling curve because it's named after this man, David Keeling. What you'll notice about the curve is it's progressively increasing, but every year it oscillates up and down. Do you know why it oscillates up and down every year? Yeah. The circulation of the heat, it's a great answer. The circulation of the heat is related to it, but it's not quite the reason why there's an oscillation every year. Yeah. Yeah, did everyone hear that? In winter, all the plants have lost their leaves, he said. In winter, there's not as much carbon dioxide. In the spring and summer, all the plants have bloomed, right? They're taking carbon dioxide out of the atmosphere because they're growing, and so the carbon dioxide drops in the summer and rises in the winter. And so Keeling even tells us, for the first time we were witnessing for the first time nature's withdrawing CO2 from the air for plant growth during the summer and returning it each succeeding winter to the atmosphere. So this is the Keeling curve in Hawaii. Now, this is a general result. So if you look at a map of the world, here's Mauna Loa. It's in the northern hemisphere. If you now go to the southern hemisphere, New Zealand, you can make the same measurements. Those measurements are shown by the red curve. So the red curve is mimicking the other curve. So it's not just a result in one place. This is true everywhere. The climate scientists will tell you that there are fewer oscillations in the southern hemisphere. And the reason for that is if you look at where New Zealand is, it's mostly surrounded by water. So there are fewer plants. Therefore, you get much less of an oscillation in the southern hemisphere than the northern hemisphere. That's a generic feature. So this has been showing that 1960, there were about 330 parts per million. Oh, that's the other way the scientist says. If you had 1 million molecules of air, 1 million molecules of air, about 300 of them were CO2 in 1959. Today, it's about 420, so it's gone up. Now, that might not sound like a big change. We'll try to illustrate to you by demonstrations why people think that that is something we need to be concerned with. Now, scientists know a lot about the past. They're very good detectives. If you like detective works, there's some scientists who are very good about understanding the human past. And so they've made measurements of the CO2 concentration back millions of years. I'm just showing you the last 10,000 years. Okay, 10,000 years is a long time. If you ask, you might ask how they do it. They drill into ice. So if you're a skier and you like ice, scientists and engineers have drilled down 2 miles into the ice to collect ice from a long time ago, and they can make measurements that help tell them about the past climate. This is one of I think the deepest one ever taken. Okay, but the point is, agriculture began about 10,000 years ago. So the first time we had organized agriculture for people, 10,000 years ago. The CO2 concentration, about 270 on this graph. The Romans, 2,000 years ago, right? The number was only a little higher. The Industrial Revolution, 150 years ago. And the CO2 concentration in the Keeling curve is this end here. That's the Keeling curve. So in a very short time, there's been a big change to the amount of CO2 in the atmosphere, and that's what we read about in the paper where people ask us to think about what might be taking place and why. Of course, there's a lot of activity, industrial activity, cars that we drive, other things that contribute to it, so I'll ask you about that. And in order to understand it, we have to say something more about the energy that we're just the children, that the energy that's coming from the sun to the earth. Now, we're not going to use this term too much, but in the newspaper you hear about the so-called greenhouse effect, the fact that the earth is getting warmer in the sense of a greenhouse. We'll try to illustrate to you why these ideas are the way they are. And in order to do that, you have to realize that just like we just saw the children, energy gets delivered to the earth, and then energy is reflected back out into outer space. And we want to know something more about that energy. So we're going to do another demonstration to illustrate to you something about the energy that comes from the sun, which you think about as visible light. All right? So Paul here has a nice demonstration that's going to start with white light. It's just a flashlight. That's an image of a flashlight. And then he's going to place in front of it a prism, show everyone the prism. There's a prism that you use in science demonstrations. And he's going to place it in front of the white light. And what you see is that inside the white light are many features of pieces that make up white light. You see red, orange, yellow, green, blue, purple. They're part of white light. They're what are called the visible spectrum. Paul is doing the same kind of experiment, reflecting it off another surface, and you see on the ceiling or on the sidewall all these colors that were originally, you think about them as white light, but when they interact with the material, you can separate out the different features of the light that we call the different wavelengths in white light. And again, you can see the red, orange, yellow, green, blue, purple. Okay, perfect. So, Paul, so that's the most important thing. Now you've witnessed that in white light are many parts of what we call the visible spectrum. And if you put on your glasses and look at any of the lights on the wall, you'll see that white light, which you think about as allowing you to just do your daily life, it's made up of many different colors. If you read the program, by the way, you can use these glasses or something like it to make colored chocolate by melting the chocolate on the glass and forming a little pattern. Read in the program, we give you little instructions for how to turn this into something more fun. Okay, so you've all seen this before because you've all seen places where you get the rainbow. You're now seeing for yourself that if you have special glasses, you can see that white light is made up of many different what we'll call other wavelengths. And the way you talk about this in a science class is your science teacher will tell you about the so-called electromagnetic spectrum, that in the visible light, what we see as white light, there are all these other colors. and those sit here in what's called the visible light. And we, as people and animals, evolved because we had to be able to take advantage of this light. But there's some parts of this that we can't see. They're not visible to us. We don't have eyes and sensors that can see them, but they're present. The ones to the left of red are called the infrared. The ones to the right of the purple are called ultraviolet. We can't see them, but we can detect them. So this feature is called the electromagnetic spectrum, and it just turns out for science reasons we talked to you offline about, we talk about them as having different distances, or the scientists would say different wavelengths associated with them. The sun is responsible for the visible light. This infrared part, which you can't see, is what Earth is radiating if you look at it from space. And to show you, to give you now a set of demonstrations that this is real and that this has an effect on materials, including CO2, we now have a set of demonstrations that walk you from this picture to everyday life. All right, and that goes like this. Oh, the first thing we have is we have a special camera. It's courtesy of the Fluor Corporation and a man named Michael Rosselli. It picks up infrared radiation. You can't see it. So we're going to point it at you and show you what you look like in an infrared camera. You know what you look like to your friends. This is what you look like if someone said, what are the wavelengths you can't see telling you about you? Okay, so you are all giving off infrared energy. You can't see it. The camera can see it. It's telling you something about the temperature that your bodies are at. Where it's warmer, you see it as brighter. Where it's less warm, it's darker. Do the following thing. Take your hand, if you see yourself, take your hand, press it against your chest, count to 3, then remove it. And you see you've left an imprint. You've left a thermal imprint on yourself just from the heat of your body. So we want, should we try it here? Yeah. So, okay, so the first thing we want you to appreciate is that every object is radiating. We tend to, at the temperatures we're at, we radiate in what's called the infrared, and the camera is helping you see it. Okay, everyone appreciate that? It's pretty cool. All right, so now, okay, so now we get to try to explore why this is relevant to our world. Okay, so up front, we have, Nikki and Paul have set this up. We have, what are they called again? Hot plates. Hot plates. The one on the left is off. The one on the right, what do you think? On. It's on. You see it's on because of what? It's turning red. It's visible. You see the color, okay? So the one on the right is clearly on. And do you think it's hot or cold? Hot. You might even say it's how hot? Red hot. All right, so now we're going to turn it off. That's the right sequence, right? Yeah. Okay, now we're going to turn it off. And I want you to tell me what you think about the two. Neither of them are having any electricity to them. They're starting to look pretty normal to our eyes. Do you agree? Okay. On the other hand, the infrared camera is going to tell us what it thinks. So this one is off. That's the one on the left. This is the one that was on. So the infrared camera still sees that it's warm. In fact, it's actually very hot. If you ask the infrared camera, there's a color code here. The yellow is probably telling you it's a couple hundred degrees, 260 degrees centigrade. So that would be 480 degrees Fahrenheit, something like that. If I did that right. If I didn't, that's embarrassing, but that's okay. So it's still very hot. It's giving off infrared energy. Okay, so now the next thing we're going to show you is that you see things, that's the visible. You also now get a signature of the infrared energy. So Nikki has a piece of plain plastic. Can you see Nikki through the plastic? That means visible light is passing through the plastic. Okay, Nikki's going to place the piece of plastic in front of the hot plate. Can you see the hot plate anymore? No. It has the same temperature as the surroundings. That tells you that infrared energy does not get through the plate. The plate allows visible light through. It does not allow infrared energy through. Do you see that? If you look down directly at it, you can see the hot plate. Visible light gets through it. The camera can't see it. So the infrared energy does not pass through the plate. Is that clear? Is that cool? Okay, watch this. Okay, Nikki has another trick up her sleeve. This is a piece of black plastic. If she puts it in front of her face, can you see Nikki? No. Visible light does not get through the black plastic. Nikki's now going to put this in front of the hot plate. What? This material does not let visible light through it, but it does let infrared energy pass through it. So the reason when we read in the paper about different effects are because different molecules have different effects on the kinds of radiation that surround us in the world. And these are just two ordinary materials. For the scientists in the room, my group tells me that the black plastic is polyethylene, and the white clear plastic is called polymethyl methacrylate. They're different molecules. Okay, wasn't that great? All right, so now is the link to the atmosphere. Our atmosphere has in it mostly nitrogen and a small amount of carbon dioxide. The reason people pay attention to the amount of carbon dioxide, we're now going to illustrate with this demonstration. We're now going to try to link this demonstration to the materials relevant to Earth. And for us, it's the atmosphere that protects us, that surrounds our planet. So here we go. We have in front another hot plate. It's very hot. You can see it's very hot because here's what the infrared camera sees. It's 100 degrees centigrade. That's hot enough to boil water. Okay? Nikki has a bag. That bag is filled with nitrogen. Okay? It's the black bag. So the black bag does not let visible light through. But what does it let through? Infrared energy. So she's going to place it in front of the hot plate, and the camera is going to measure what temperature it thinks it's seeing. So the camera, which is where Paul is collecting energy. And the camera thinks that it's collecting energy equivalent to 83 degrees centigrade. Okay? That energy is starting at the hot plate, passing through the bag, and reaching Paul's camera. And Janine just wrote, if it's N2 in the bag, it's 83 degrees centigrade. Now Nikki's going to do the same experiment, but inside the bag is CO2, carbon dioxide. Okay? A different gas. So now she places a bag of carbon dioxide in front. Again, you see the infrared energy gets through the bag. Visible light doesn't. But what's the temperature? Call it 78 or 79 degrees centigrade. Okay? That's when you have CO2. Okay, now you have to put on your thinking cap. Which is bigger, 83 or 78? 83 is bigger than 78. They both were started with the same energy at the hot plate. So what this tells you is the following thing. The camera receives less energy when you have CO2. Where did that energy go? It went into the bag that has the CO2. So this demonstration shows you that CO2 is taking up some of the energy from the hot plate because it didn't get to the camera. So this demonstration makes it very clear that CO2 in the atmosphere has a very different effect than nitrogen. That's what this was meant to show. Do you see that? Wasn't that cool? All right. So CO2 is a molecule that looks a little like that doesn't always smile at you. Nitrogen is on the left. What this experiment is saying is because CO2 is taking up energy, what it's telling you is that when infrared energy comes from the Earth and hits these molecules, the CO2 gets really excited because it takes up all this energy. Okay, so what we now need the children to do is come help us, show us what it means for irradiated CO2 to do a CO2 dance. Okay, so can anyone that wants to do a dance can come on down, including parents, I suppose. Okay, so anyone else want to do the CO2 dance with us? Yeah, come on down. All right, so I need you all to look at the screen. Okay, I need everyone to look at the screen. So you know this, when you eat chocolate, you take in energy, right? Yeah. And when you take in energy, what do you feel like doing? Running. Yeah, running. You feel like you take up a lot of energy, right? So when things take up energy, they move a lot faster. And so CO2, we just saw, absorbs infrared energy, okay? Now this is what CO2 looks like. It's one carbon and two oxygens. And it can do different vibrations, so-called vibrations. It can vibrate back and forth, but when it absorbs infrared energy, it does what Janine and I are going to do, right? When it absorbs infrared energy, it does this, right? Okay, so give yourself some space, turn around and face your parents, and if we irradiate you with infrared energy, what does the CO2 molecule do? And that, everyone, is the CO2 dance. What do you think? That's good? Okay, back to your parents. Okay. All right. We've just tried to illustrate to you a very important feature of the environment because of the kinds of effects that we've been talking about. Now, there's a history of this. You might think, because you read it in the paper, that this is a recent history. But it's actually a very old history. And until recently, this slide would have been thought of as the actual history of CO2 and energy, so-called energy absorption. Until recently, it was believed that a great chemist, John Tyndall, an English chemist, was the first to connect carbon dioxide and water vapor to absorbing infrared energy. What we know about ideas linked to climate change is that 130 years ago, a very famous Swedish chemist won the Nobel Prize in Chemistry, named Svante Arrhenius. He made a prediction for if you change the amount of CO2 in the atmosphere, he suggested you would change the temperature of the atmosphere. And his prediction already 130 years ago was consistent with what modern scientists think. And if you learn in school something in chemistry, you'll run across this name Arrhenius. But the fact is, and in the olden days, they didn't say carbon dioxide. In the olden days, they said carbonic acid. That was the name given to CO2. Now, about 10 years ago, historians discovered that, in fact, John Tyndall was not the first person to note this effect. In fact, it was an American scientist, an American woman, in fact, named Eunice Foote. No known photograph of her exists. And she was the first person to make this connection of CO2 and absorbing energy from the sun. And in fact, if you like this kind of thing, reading old papers, here's her paper. Written in 1856, 3 years before John Tyndall, she makes 2 points. Among the number of points she says, thirdly, the highest effect of the sun's rays I have found to be on carbonic acid. That's CO2. She then goes on to conclude in this short paper that an atmosphere of that gas, CO2, gives to our Earth a high temperature, and even predicts that if it were an increased amount of it, it would have an increased temperature would result from its effect. She was sort of lost to history. In fact, this paper was presented to the American Science Organization. She was not the presenter. I don't know the full history about it, but there is a Princeton connection because the person who presented it was a great scientist, one of America's early great scientists, John Henry. He's the one apparently who read her paper to the community of scientists, and he had no idea, of course, what he was reading. And so this article for a long time was lost to history until it was rediscovered. So there's a wonderful example of early independent work by great independent thinkers. Hope you found that interesting. And okay. So this is a quiz for the children. There's CO2 in our atmosphere. Where does it come from? Some of it comes from us. That's true. So the background CO2 in the room, there are in a million molecules of gas, there are about 400 CO2 molecules. But when you and I breathe out, the air we breathe out is 40,000 CO2 molecules per 100. So when you sit in a room like this, the CO2 concentration has been increasing just because we're breathing. If you're interested in that, by the way, I have a CO2 monitor in front of the room, and we can see what it says about whether or not you were breathing or not during this lecture. But where else does CO2 come from? Yeah, hand all the way back. Cars, excellent. Over there? Yeah. Again? Yeah, greenhouse gases are incredibly important. Yep, young man in purple and then young lady in red, or vice versa. Factories, yep, young man in purple. Yeah. Yeah, big factories. Young lady in purple over here. Oh, I couldn't hear that. Yeah, cooking and heating. Yeah, so you got pretty much everything. Our modern life is filled with CO2 coming from all kinds of activities, most of them burning fossil fuels, gasoline in cars or airplanes. But of course, if you burn down forests, burn down trees, and cows, sort of fart and things like that. But where do fossil fuels really come from? What's the origin of the fossil fuel? Yeah, plant matter that was buried millennia ago was first living materials that after they died, that's the ultimate origin of it. Okay, so this might be a bit for the parents, but if you want to now see the history of the last, 60 years, it's shown here. On the left is 90 degrees south, that's the South Pole. Here's the equator. On the 90-degree north, that's the North Pole. This data starts in 1979. On the vertical is the CO2 concentration, and there's another history taking place on the right. So if you play this video, what you'll see is that over these 50 years, more than 50 years, the CO2 concentration has been continually increasing. Just like the Keeling curve tells us, there are oscillations. Everything is going up in both the northern and southern hemisphere, but there are more oscillations in the northern hemisphere. And we're getting up today to on the order of 420 parts per million CO2. And the demonstrations have tried to point out to you why there's a link between CO2 and energy, or CO2 and temperature. Okay, this is a nice video.
Why is there more fluctuations in the north?
Okay, so the question is, why are there more oscillations in the northern hemisphere? And we tried to point a little of that out when we discussed the Keeling curve. We pointed out the oscillations. I think you were the one that answered the question, by the way. The oscillations are tied to the seasons, that the plant growth is in the spring and summer. The plants take CO2 out of the atmosphere. In the winter, the plants have lost all their leaves, and so CO2 is returned to the atmosphere. And so the oscillation is due to kind of living plants, and there are fewer of them in the southern hemisphere. Okay, so fortunately for us, the Earth has an ocean, and the ocean plays an important role in setting the climate that we experience. So this next bit is to tell you a little about one effect of the ocean. The ocean is this massive body of water. Now, we're going to show you why scientists state that the ocean absorbs energy, and it does so in a way that a scientist would try to measure how much heat it's able to absorb. They sometimes talk about that as heat capacity. So to illustrate that, we have two balloons on the left. We're going to put a flame under each of them, okay? But one of the balloons has some water in it. They both have a lot of air, but one of them has water in it. How can you tell which one has water in it? Young lady. Yeah, why not? You put your hand up. It looks like it weighs a little more. Which one looks like it weighs a little more? Left or right? Okay, maybe. Okay. So, yeah, so one thing is you could try to weigh it. Okay, someone else? Lady in back? Yeah. Okay, so we have another, it's good, you're trying to figure it out. Another way to think about it. So it's not obvious which one has water, except we have an infrared camera. And I pointed out earlier that not only does CO2 take up infrared energy, but it turns out so does water. So we're going to point the infrared camera at the two balloons, and let's see what you see. So here's the left balloon. Here's the right balloon. Which one has water? Yeah, there's the water. The water absorbs infrared energy. So the next thing you also read in the paper is water vapor has a big effect on our climate. Why? Because it is also a so-called greenhouse gas, as people talked about. It's actually the most important one because of this kind of effect. Okay, so now we're going to try to pop the balloons and by heating them, and we'll try to see the way that water helps keep a system, if you like, more neutral. So we have a flame. Janine's lighting a fire below each of them. They're both at the same height, so we're going to slowly lower them to get them closer to the source of heat. What do you think happens to a balloon when it's heated? Paul, you're a little ahead, but that's okay. So the one without water popped. The one with water is perfectly fine for quite a while because the water is taking up most of the energy and the balloon doesn't get so hot. Okay, so our ocean is a big influence on the climate that's taking place. Okay, thanks, Paul. Thanks, Nikki. Okay. So finally, I'll just comment that all the way at the beginning, people talked about ice. So I just want to make 2 points about ice. Not all ice is the same from the standpoint of what happens if the temperatures in our world go up. So there's ice that's floating. You think about those as icebergs. You think about it as what's called sea ice. That's floating ice. What you can be sure of is that if you see floating ice, there's more ice below the surface that you can't see. Okay? But it's floating. Okay? It's free from land. But there's other ice that's on land, like the glaciers, if any of you have been to the famous glaciers in the world. Or there are things that are called ice bridges. They're big shelves of ice. This is an enormous shelf of ice. These are people. They're connected to land. Okay? So there are two different kinds of ice. That ice that's free in the ocean, that ice that's on land. And there's a big difference now when they melt. So Janine has done the following experiment that probes sea level. So here's an experiment where she has ice and she adds water. This ice is floating. It's like a glacier. It's floating ice in the ocean. This ice is on land. It's tied to the land, same amount of ice. And now you ask, what happens to the sea level? Janine's going to put a little mark here. What happens to the sea level when all the ice melts? And on the left, what happens to the sea level? Does it change? No, the floating ice, when it melts, doesn't change the sea level. But when ice is on land, what happens to the sea level? It goes higher, a lot higher when the ice melts. So in the paper, when you have to read, you have to be aware of these distinctions as you think about what are possible impacts of things we are doing to our environment. Okay, and here's a little video from NASA we'll close with. So I think we can all thank NASA for having her eyes on the planet to all help us plan our future. Okay, so there are things we can do, of course. We can think about the way we utilize energy and the choices we have to make as a society. So this just says things you read about in the paper. You know, people now are thinking about different sustainable sources of energy, whether it's running water, hydroelectricity, or the solar energy farms you sometimes see on the side of the road, or wind energy, or geothermal energy that's present, nuclear power, you know, say nuclear fission, or maybe in the future nuclear fusion, and all the electrification. For example, maybe you came here in an electric car. So there are different kinds of ideas now we have to think about as individuals in a society. And that brings me to the end of our show. We tried to share with you that, you know, we're living on Earth. It's our only home. Scientists make measurements to try to understand the world that we live in, the world of the past, and also perhaps the world of the future. We've talked about the role of the sun, the atmosphere, the ocean, and ice. We've talked about some of the effects of the different molecules, in particular CO2. And we just briefly mentioned that the future will depend on the choices we make of the kinds of energy we use. I should say that this talk was only possible because of a great team. Janine Nunes, who's here, Nikki Abbasi, Paul Canillo, who walked out the back, and Dan Steinberg. The idea for this lecture came from Michael Faraday. If you're a young person, you'll read about Michael Faraday. He gave many lectures of this style in the 20th century, in the 19th century, I'm sorry, I'm all confused. We got help from Nader Javanji, a scientist at the Geophysical Fluid Dynamics Laboratory in Princeton, from Rob Sokolow and Gabe Vecchi, who are professors here at Princeton. We had help from colleagues at Harvard to do this. We want to wish you a safe and happy holiday season, and if anyone wants to talk to us, we can hang around for a while. Have a wonderful day.
You want to go? And in this mix, they usually include nuclear fission.
So what do we see? It's temperature, right?
Oh, that's huge! But think about like your hand when it gets warm. That's like what you call a sensor. So the camera has that inside. Okay, this was the first show in the morning. Then that's